Good morning, everyone. So welcome in the third day of the conference. And the first talk will be given by Igors Gorbovickis from Jacobs University Bremen. He will tell us about the combinatorial structure of the renormalization attractor for multicritical circle maps. So,
thank you for the introduction, and thank you to the organizers for giving me the opportunity to speak at the conference. So it's a great pleasure to be in Będlewo. So I'm going to talk about combinatorial structure of the renormalization attractor for multicritical circle maps. This is joint work with Michael Jampolsky. Well, as you can see from the title of the talk, the main object of the talk is going to be multicritical circle maps. So let me check how it, okay, so it works. Yes, so multicritical circle maps, well, first of all, for me, the circle will be the affine manifold R mod Z, and a multicritical circle map is, well, first of all my maps in this talk are going to be analytic. So in particular, I'll be looking at analytic multicritical circle maps, and these are orientation preserving analytic homeomorphisms of the circle that have several critical points. So since the maps are analytic, then we can say what's the local structure of the map around the critical point. So locally around the critical point, it's a composition. So it's the composition here. F is, well, first some locally conformal map phi, then the power map QD, which is essentially x to the power d, and then composed with another locally conformal map. And the power d is called the critical exponent. And since the maps are analytic, the critical exponent must be an odd integer. And for simplicity in this talk, I will always assume that this odd integer is equal to 3. So the critical exponent is equal to 3. Although everything I'm going to talk about will work for any other odd integer critical exponent. So the whole discussion of my talk will be motivated by the attempt to understand various universality phenomena for multicritical circle maps via hyperbolicity of renormalization. So in other words, the main motivation is hyperbolicity of renormalization. Before talking about the general case of multicritical circle maps, I'll talk about a special case of the so-called unicritical or just critical circle maps. So the case when there is only one critical point. So in a sense, we are trying to make a move from one critical point to, well, several critical points, essentially as many as we like. And the case of the unicritical case is well studied. Let me start by reviewing some results about unicritical circle maps, the relevant ones for this talk. So, and I will start with the so-called golden mean universality for unicritical circle maps, which is probably one of the simplest universality phenomena we can describe. It's analogous to the Feigenbaum-Collet-Tresset universality for unimodal maps. So, okay, not supposed to be like that. Okay, so this particular slide for some reason does not show up well. Yes, well, the next one is fine. Well, I can proceed with the next one. So that slide luckily was not so important. So I was just defining the golden mean, which is √5 minus 1 divided by 2, which can be expressed as a continued fraction. So that was the slide where the continued fraction was written out explicitly, but I guess everyone knows what a continued fraction is. So the golden mean, well, so it's 1 divided by 1 plus 1 divided by 1 plus, and so on, infinitely, and infinitely far down on the diagonal. So, well, okay, I can write it down. So 1, 1 plus 1, and so on. So these numbers 1, so a continued fraction will be encoded by a sequence of these digits written in square brackets. And this is what you see right now on the slide. So this is the golden mean. And we will consider the so-called nth convergence of an irrational number, in this case of the golden mean. So we'll denote them by Pn over Qn. So these are just finite parts of the continued fraction. So let me explain the universality phenomenon. So assume we have a smooth family of unicritical circle maps with a fixed critical exponent. So just one critical point and fixed critical exponent d. And we assume a certain monotonicity property that the partial derivative with respect to theta is positive at any point of the circle. And in that case, yeah, so we're interested in the dependence of the rotation number of the map f theta on the parameter theta. And it's well known that in that case, the graph that we see is a Dale staircase with plateaus at all rational values of the rotation number. So a typical picture is here on the right. And let's find the parameter theta, well, denoted by theta star, for which the rotation number is equal to the golden mean. So again, this is here on the picture. And we consider the nth convergence, Pn over Qn, and the corresponding plateaus, so the intervals on which these rational rotation numbers are obtained. So we denote them by In. So as n goes towards infinity, these intervals accumulate to the parameter theta, and they jump from different sides. Here is I1, here's I2, then I3 on the other side, and I4 on the opposite side, and so on. They accumulate to theta star. And we could be interested in the quotient of the lengths of the successive intervals in this sequence. So In divided by In plus 1. And as we pass to the limit, first of all, the limit turns out to exist. And second, it equals to a universal constant delta. So universal in the sense that it does not depend on a particular family. So it does not depend on a particular family f theta that we choose. It only depends on the critical exponent d. And since in this talk, we always consider the critical exponents to be equal to 3, so in particular, delta of 3 is approximately, well, this number. So this is an example of a universality phenomenon that that we consider. And next, I would like to explain, well, I would like to give an explanation of this universality phenomenon via hyperbolicity of renormalization. So again, my explanation will be based on a picture, but before, well, so not, it's a little bit of hand waving, not precise. So at this point, I haven't defined what renormalization is. And for the explanation that I'm going to give, the only thing we need to know about renormalization is that renormalization is a certain, well, nonlinear operator acting on a space of circle maps, well, critical circle maps. And so we don't need to know the definition, the exact definition of the renormalization, but we need to know how it acts on the rotation numbers. So it acts on the rotation numbers as the Gauss map. So if the rotation number is expressed in a continued fraction like that, then after applying renormalization, the first digit of the continued fraction disappears, and we start just with R2, R3, and so on. Okay, so here's the picture, and let me explain the picture. So this is my attempt to give a, well, two-dimensional picture of an infinite dimensional space. So the phase space is the space of circle maps, which is of course infinite dimensional. And let's assume that we have a fixed point of the renormalization operator, f star. So it's here. Renormalization of f star is f star itself. And the rotation number of f star is the golden mean. So we assume that f star is a hyperbolic fixed point with a one-dimensional unstable manifold. So here it is on the picture. So it's one-dimensional, and it means that the corresponding stable manifold is of codimension 1, so it's infinite dimensional. And we assume that for any other unicritical circle map F with the golden mean rotation number, it belongs to the stable manifold. So, okay, so I probably can move this somewhere, or I cannot. So here, this is the stable manifold. So in particular, it means that the stable manifold is a global object, and there are no other fixed points of renormalization with the same rotation, well, with the same golden mean rotation number. And now if we have a family F theta, well, let me first talk about these blue strips. So these blue strips are the maps with rotation numbers equal to the nth convergence. So here it's the rational rotation number whose continued fraction consists of one digit 1, then 2 digits 1, 1, and 3 digits 1, 1, and so on. Since the rotation numbers of the maps on the stable manifold are golden mean, then it means that these blue strips accumulate to the stable manifold. And renormalization, we know how it acts on the rotation numbers. It just forgets the first digit. So it means that renormalization takes well, this strip into the one further to the left from the stable manifold. So now if we have some one parameter family, the red one, the monotonicity condition implies that it intersects the stable manifold transversally. And then due to hyperbolicity of the fixed point, we see that, well, so these intervals of intersection with the blue strips are precisely the intervals I1, I2, I3 that we were interested in the universality phenomenon. And due to hyperbolicity of the fixed point F theta, we see that once we get closer and closer to the stable manifold, the ratios of the consecutive red intervals are going to be equal to the unstable eigenvalue corresponding to this one-dimensional unstable manifold. And in this picture, now you can see that it doesn't matter if I choose another family, another one parameter family of unicritical circle maps somewhere far away from this one. As long as it intersects the stable manifold transversally, the same argument works. And this is the explanation of universality. This is why the limit of the consecutive, the ratios of the consecutive intervals is independent from a particular family. Okay, so maybe I can stop here for a moment. Any questions? Okay, so this is a motivational, well, in some sense, a motivational part of the talk. And well, there are various other kinds of universality phenomena corresponding to other rotation numbers. And so in this talk, I will focus only on rotation numbers of bounded type. So the rotation numbers of bounded type are the ones where if you represent them as a continued fraction, so it's an infinite continued fraction, it's an irrational rotation number with an infinite continued fraction, of course. And if all elements, all digits in the continued fraction are bounded by some uniform constant b, then we say that this rotation number is of bounded type, so of type bounded by b. So this is equivalent to a certain Diophantine condition. So let me not focus on that too much now. But in order to explain various other kinds of universality, in the late 1980s, Lanford stated the so-called renormalization hyperbolicity conjecture for unicritical circle maps. So I'm going to state it now again in the setup for rotation numbers of bounded type. I will disregard unbounded type. So the conjecture, well, I split it into two parts. First of all, the first part is the existence of the global horseshoe attractor. So one feature of the previous picture was that the fixed point F star was a global, it was a unique fixed point which was attracting all, all other maps with the same rotation number. So similarly here, if we have two unicritical circle maps with the same irrational rotation number, then their consecutive renormalizations should get closer and closer to each other. And then, well, there will be some attracting set. A certain R invariant attracting set, which we denote by AB. On the attractor, on the attracting set, the renormalization operator is topologically conjugate to the right shift on the bi-infinite sequence of numbers. So the numbers are from 1 to b, so corresponding to the bound on the bounded type. So the conjugacy here is given by this map I, and so the digits in the bi-infinite sequence of numbers. So, well, every element of the attractor is encoded by a bi-infinite sequence of numbers, and the relation between these bi-infinite sequences of numbers and the rotation numbers is the following. So if we have an encoding of an element of the attractor with bi-infinite sequence of numbers, then if we look at the right part of this bi-infinite sequence, so starting from R0, it will give the rotation number of F, of an element of the attractor. So the second part of the conjecture is that actually this attractor is uniformly hyperbolic with a one-dimensional unstable direction. So in this talk, I will focus on the first part of this conjecture. And our goal in general is to generalize this. Well, first of all, this conjecture for unicritical maps is settled. I'll mention the result in the next slide. So our goal is to generalize this conjecture to multicritical circle maps. So for an arbitrary number of critical points. Today I will focus on the first part of the conjecture, and particularly the structure of the attractor for multicritical circle maps. So, the result is essentially that in the unicritical case, the renormalization hyperbolicity conjecture is proven in a series of works by Deferry and De Mello, and also by Yampolsky, and this has been done in the late 1990s, early 2000s. And now back to the renormalization hyperbolicity conjecture, I would like to make a few observations. So first observation is that the renormalization operator is bijective on the attractor because it's conjugate to the right shift on the bi-infinite sequences of numbers. So we're essentially just shifting the sequence to the right or to the left. We're not losing any information. So it's renormalization is bijective on the attractor. So second, The word combinatorics appears in my talk, and I have not mentioned this yet. So for me, everything good with the sound? Okay. Yes, so combinatorics. So what do I mean by combinatorics? Well, by combinatorics, I mean the relative position on the circle of the points of the points of the critical orbits. So in the unicritical case, we have only one critical point, so we have only one critical orbit, and then the relative positions of the points of that orbit are defined by the rotation number. So in the unicritical case, the combinatorics of a map is completely described by its rotation number. In the multicritical case, it will be more complicated because we'll have several critical orbits, and we'll have to talk about their relative position. The third observation here that we can make is that every point of the attractor is determined by this by infinite, well, we can call it by infinite combinatorics. So I'm using this term by infinite combinatorics because it's a by infinite sequence of numbers, but it's related to the rotation number. So in other words, when I say that the point of the attractor is determined by infinite combinatorics, in particular, I mean that if we have two different points of the attractor, well, the right parts of their by infinite sequences can match, which means that they have the same rotation number and they have the same combinatorics. But if these are two different points of the attractor, then somewhere in the backwards, so in the left part of the sequence, there will be differences. So it means that if we, well, since the renormalization on the attractor is bijective, we can backwards renormalize. So we can backwards renormalize to some point when the rotation numbers will be different, so the combinatorics will be different. So this is what I mean by saying that every point of the attractor is determined by its by infinite combinatorics. So the main result of this talk is that this third observation actually does not hold for multicritical circle maps in case if we have at least 3 critical points. So two additional critical points compared to the unicritical case. So in the remaining time, I'll try to explain where this phenomenon comes from. So yes, it has to do with extra critical points. And so before actually going into in depth in the explanation, I should probably talk more about the unicritical case and first explain how the attractor is constructed in the unicritical case, and then we'll see what is different when we have more critical points. So at this point, it's probably time to actually define the renormalization operator. In general terms, the renormalization operator is a rescaled first return map to an appropriately chosen domain. So following this idea, we'll have to choose an appropriate domain. So in this picture that you see, the horizontal line, so this one, is the part of the circle. 0. So right now we are still talking about the unicritical case. So 0 is the unique critical point, and rho of f is the rotation number. And if we look at the nth convergence, written as an irreducible fraction Pn over Qn, and we look at Qn's, these are the closest return times. So in particular, we can consider an arc on the circle with the endpoints fqn plus 1 of 0 and fqn of 0. So this arc on the circle will be my domain on which I'm going to consider the first return map. And it's not so difficult to check that the first return map is going to be piecewise defined. So on the red interval, it's going to be FQN. And on the green interval, it's going to be FQN plus 1. So this is the first return map. And well, now we need to rescale in order to get renormalization. So the rescaling works this way. We want to rescale the whole picture so that the green interval, the larger one, would be the interval with endpoints 0 and 1. So the rescaling is then given by this map, the affine map H. So this will give me the nth renormalization of the unicritical circle map F. And well, the problem that we see here is that, well, as a result of renormalization, we're not getting a circle map. So what can we do about this? Well, we can attempt to make it into a circle map by gluing the interval into a circle. So we can use, so here instead of the iterates of F, I wrote psi and eta. So psi and eta form the so-called critical commuting pair. So a pair of maps that commutes and both having critical points at 0. So we can try using the red one, psi, as a well to glue the interval along the map psi into a circle. So this can be done, and then the critical commuting pair projects, or more precisely, this piecewise defined map projects into a map of a topological circle. So when we glue, we get a topological circle. We'll get a map which will be which will have a critical point at 0. But the problem is that we will not have a canonical affine structure on the circle that we obtain. So it's more that we're getting a conjugacy class of critical circle maps, but not a particular critical circle map. And this is a problem, and this is why, at least in the classical theory, people don't glue and work with critical commuting pairs. Well, actually, one good thing that we can still get from this gluing procedure is that we can define the rotation number of a critical commuting pair. So the rotation number of the critical commuting pair will be the rotation number of the circle map that we obtain by the gluing. Of course, the rotation number is independent of the conjugacy, so the rotation number is invariant in the conjugacy class. So that would be a valid definition of the rotation number of critical commuting pair. So one can also renormalize critical commuting pairs instead of just starting with the circle maps. So if we have a critical commuting pair, the renormalization works as follows. So we take the red interval onto here, and then we apply the map eta to this red interval until it covers the point 0. And then after that, we forget about the right part of the picture. So from this vertical line, we forget about the right part of the picture, and we obtain the new critical commuting pair where the red interval is taken onto this one, and this part of the green interval is taken wherever by the same map eta. Okay, and then rescaling, of course. So then we rescale this picture to the appropriate size. So such renormalization of critical commuting pairs matches with the renormalization of the critical circle maps. And in particular, this is an easy way also to define the rotation number, or well, to look at the rotation number of a critical commuting pair. So the number of jumps, the number of times I need to apply eta here in this sequence, if it's equal, well, it's called the height of the pair. So if it's equal to R, so the number of times we need to apply eta, then we can compute the height of the renormalization, then the height of the next renormalization, and so on. So we get a sequence of heights, and the sequence of heights will be the rotation number of the critical commuting pair. Well, the corresponding continued fraction that consists of these heights. And now you can see that indeed the renormalization acts on the rotation numbers as the Gauss map. So indeed, if we renormalize the critical commuting pair, this corresponds to just forgetting the first height in this sequence. So indeed, the picture, the hyperbolicity picture that I showed you, stays valid. And okay, so now we now that we know how we renormalize commuting pairs, I'll say a few words about how the attractor is constructed. So the first step is the so-called complex a priori bounds. So again, I state everything in bounded type. So in bounded type, complex a priori bounds for unicritical circle maps were obtained by De Faria, I think in his thesis. And and the general idea and the general structure of this construction follows a similar one for renormalizations of unimodal maps. Complex a priori bounds say that if we start with some analytic critical circle, critical commuting pair, then after sufficiently many renormalizations, it can be extended to the so-called holomorphic commuting pair, which is an analog of polynomial-like maps. And so here's the picture. So what is it? So a holomorphic commuting pair. So here in the picture, you can see the green interval and the red interval. So this is essentially, well, the critical commuting pair. And then it extends to the complex plane as follows. So we have, so the green map extends to a map on some region like that, the red one to the region like that. So we have some butterfly. And the extension is done in such a way that the wings of the butterfly are mapped univalently onto this large round domain, but with some slits along the real line. So we'll have to cut out for each of the two maps. We'll have to cut out some slits on the right and on the left. But otherwise, on the remaining part, it's a univalent map onto this larger round domain. And the third map here in the middle is the composition of eta and psi. And since eta and psi commute, doesn't matter in which order we compose. And the third domain here in the middle then is mapped onto the larger one, again with some slits on the right and on the left, as a 3-to-1 branched covering with a branching point at 0. So this is what we call, so if we have something like that, we call it a holomorphic commuting pair. And the complex a priori bounds say that we can, after sufficiently many renormalizations, we get such a picture. And the modulus of this picture is uniformly bounded away from 0, so definite modulus. And by modulus, I mean the modulus of the annulus between the domain, so the wings of the butterfly, and this central domain, and the boundary of the large domain. Okay. Yes, the range can be made a circle just from the point of view of drawing pictures. If I draw a large circle, I'll have not enough space on the slide. So that's the only reason why I drew this as an ellipse. Okay, so the second part is, well, independent from essentially from the theorem about holomorphic complex bounds. The second part is that any two such holomorphic pairs with the same rotation number, they're actually quasi-conformally conjugate. And quasi-conformal conjugacy is constructed in a similar way to the hybrid equivalence for the polynomial-like maps. So in that sense, the pictures are very well, the theories are very similar. And so once we have complex bounds, so the next step is, well, in the construction of the attractor is the so-called rigidity of Macmillan towers. So I'll have to give some definitions here. So instead of renormalization, I'll have to consider the so-called pre-renormalization, which is the same renormalization without rescaling. So essentially the first return map without rescaling. I'll call it pre-normalization. I'll just write the letter P in front. So by this curvy H, I will denote the space of all holomorphic pairs satisfying complex bounds. So the ones that we obtained from the theorem for complex bounds. And a limiting tower will be an element of this product space. So essentially a bi-infinite sequence of holomorphic commuting pairs, with the condition that if we take one of those pairs somewhere in this bi-infinite sequence and pre-renormalize, restricted on the real line, we get the next one, again restricted to the real line. So so we can view a tower as follows. Let's say you have a holomorphic commuting pair of some fixed size. And first of all, you have a sequence of holomorphic commuting pairs which sit inside, like more or less a nested sequence that goes inside. But also you have a sequence of holomorphic pairs which are larger than the one we're looking at. So the previous one is larger, and then the one we're looking at is obtained from the larger one as a pre-renormalization of that larger one. And then there's a larger one and so on. So this tower of holomorphic commuting pairs eventually, so to say, covers the whole complex plane. So this is how we should think about a limiting tower. And any element of the attractor is associated to a unique limiting tower. So roughly speaking, if we have an omega limit point of the renormalization operator for some critical commuting pair, then this omega limit point, well, the neighborhood of this omega limit point is visited infinitely many times by the sequence. So we have points that are arbitrarily close to that omega limit point, which can be renormalized backwards many times. So in the limit, we obtain an element that can be renormalized both forward and backwards as many times as we like. So we get a tower. So this is approximately how we get this correspondence. So a limiting tower is an element of the attractor, and the tower rigidity theorem, which in the setup of unicritical maps was proven by Yampolsky in 2001, says that first of all, any two limiting towers with the same combinatorics are quasi-conformally conjugate, which essentially follows from the fact that holomorphic pairs with the same rotation numbers are quasi-conformally conjugate. So the whole towers are quasi-conformally conjugate. And any two quasi-conformally conjugate limiting towers are actually affinely conjugate. So they differ just by rescaling. And if we, let's say, associate this middle holomorphic pair H0 with an element of the attractor, we rescale it to the size 1. So essentially, it means that the tower, so there are no two towers with the same combinatorics. So there are no 2 points of the attractor with the same combinatorics. And so in the remaining time, I will try to show that the first part of this theorem in the set of multicritical circle maps with at least 3 critical points does not hold. So in other words, if we have 2 towers which are quasi-conformally conjugate, then they are in fact affinely conjugate, even if we have many critical points. But 2 towers with the same real combinatorics might not be quasi-conformally conjugate. So, well, maybe I should state the results more explicitly. So the first 2 theorems, which are well, from about a year ago, the first one says that if we have 2 analytic multicritical commuting pairs with the same combinatorics and an irrational rotation number of bounded type, then their successive renormalizations converge to each other exponentially fast. So a rather easy corollary, although not stated in the preprint, but the corollary is that, well, from that is that any 2 quasi-conformally conjugate limiting towers with these bi-infinite rotation numbers of bounded type are affinely conjugate, so the rigidity of the towers in that sense. And so the new result is that if the number of critical points is at least 3, then there exist 2 limiting towers that have the same combinatorics on the real line, but are not topologically conjugate. So in other words, it means that if we restrict such 2 towers just to the real line, on the real line, they will be quasi-symmetrically conjugate because of the real bounds. But the complex extensions will not be topologically conjugate. So this seems to be a new phenomenon which have not appeared previously. So let me try to give some explanation. So first of all, I will talk a little bit about description of combinatorics, well, a convenient description of combinatorics. So now, from now on, we have many critical points, at least 3. One of the critical points sits at 0, and we have 2 other free critical points, which can be somewhere, well, anywhere else. And I would like to describe combinatorics of, well, so relative positions of these 3 critical points. And a convenient way would be, well, to introduce some symbolic encoding. So if I have a critical commuting pair like that, then if the height of the pair is R, so it means that I apply the map eta R times here before I cover 0, then what I can do, I can split the green interval into subintervals. So I will enumerate them 1, 2, 3, and so on. This one will be R. And I'll have some leftovers. I'll have the red interval, which I can enumerate by 0. And this small part of the green interval, which I can enumerate, say, by -1. So if I look at the free critical point, it's somewhere here. So it will be prescribed one of these numbers from -1 to R. Well, of course, the critical point can be, at the end point of such intervals. Then, well, this problem is similar to the problem that rational numbers can be described as decimal fractions in 2 different ways. So it's So a little bit unpleasant, but we can live with that. We can just say which one which description we choose. So and then we renormalize, and we can again consider a similar splitting, a similar picture, and again look where the critical point after renormalization, in which subinterval the critical point falls, and then we can collect this sequence of intervals. So in other words, if the rotation number is R0, R1, R2, and so on, then the itinerary of a critical point can be described by a sequence of numbers where each Wj is from the set -1, 0, and so on up to Rj. Rj is somewhere here. And well, the renormalization procedure describes some restrictions. So if so Wj plus 1 is equal to 0 if and only if Wj, the previous one, is equal to -1. And the convenience of this description of combinatorics is that renormalization acts on this combinatorics by, again, forgetting the first digit, so the first W0, similarly to how it acts on the rotation numbers. And combinatorics of a commuting pair consists of, well, the rotation number and an ordered sequence of these descriptions of the critical points. So complex bounds in the multicritical case, in the case of bounded rotation numbers of bounded type, were obtained by, well, quite recently by Esteves, Mani, and Yampolsky. And the statement is similar to the unicritical case. So you, after a bunch of renormalizations, we have this extension to a multicritical holomorphic commuting pair. So what is it? So what's the difference between the regular holomorphic commuting pair? Well, we certainly have extra critical points, let's say somewhere here. So this wing of the butterfly cannot be mapped onto its image univalently. So it is rather a branched covering map with a bunch of branching points. So same for the three other maps. So extra branching points can appear, but otherwise, well, there will be a bounded number of extra branching points, of course, uniformly bounded, but otherwise the picture is the same. And well, it turns out that two multicritical holomorphic commuting pairs with the same combinatorics on the real line might not be even topologically conjugate. And in the next slide, I'll try to explain why. And the reason is that, well, we certainly know that there are critical points on the real line, but there are also unavoidable critical points in the complex plane. And so I tried to explain this on a picture. So, in order to see that, we need to see how we get holomorphic commuting pairs. And a good way of thinking about this is that, imagine, so we get holomorphic commuting pairs after a sufficiently high renormalization of the initial map. And it's convenient to view the initial map as here in the bottom picture as a necklace with beads. So the small domains that will form the holomorphic commuting pair. So the green one in the middle. So we start with the green bead in the middle, and the dynamics of this large map somehow shuffles those beads. So it's mapped to the yellow beads. And here in my picture, there's somewhere one red critical point, and somewhere else there's one blue critical point. And when the green bead returns back to itself, I put those two crosses, the red cross and the blue cross. These are the points where the critical points will be located. So the red cross, when we iterate, it eventually collects on the way this red critical point, and the blue cross eventually collects this blue critical point. And the question is in which order these red and blue critical points are going to be collected. So if first, by iterating the green bead, we first arrive to this yellow bead, then first we will collect the red critical point, and then so here is the picture. We will have a critical point here. After that, we're going to keep iterating. But if we have a critical point here, then it means that these two intervals will be mapped to the real line, right? And if they're mapped to the real line, it means, well, eventually we will collect the blue critical point. And so it will appear here, and it will also appear here and here. So this will be so we will obtain a picture like this. So the red intervals here are going to be mapped on the real line. So these are preimages of the real line. However, if we first collect the blue point, then the first on the way, the critical point will appear here. And then these intervals are taken onto the real line. And then eventually, when we will collect this other red critical point, we will get critical points here and here. And you see these two pictures are not topologically the same. So it means that these two, even though these two pairs on the real line can have the same combinatorics, the complex combinatorics is different, and they cannot be topologically conjugate. So, okay, I'm running out of time, it seems. So I probably will have to. So this is the key idea. This is the key idea, and the rest I should probably state rather quickly, although I can say much more about the remaining part as well. So how can we deal with that? Well, first of all, it turns out that if we have two critical pairs with the same real combinatorics, maybe even holomorphic pairs with the same real combinatorics, we don't know what's the complex combinatorics is. They might not be topologically conjugate, but it turns out that if we renormalize both of them sufficiently many times, then the real combinatorics, if it was the same for the two maps, it prescribes eventually the complex combinatorics as well. And this is due to the fact that when we renormalize, even if 2 critical points are very close to each other, if we renormalize sufficiently many times, then this picture with the beads should look as the beads are getting smaller and smaller, and they're getting smaller than the distance between two critical points. And then we will know, well, just based on the real combinatorics of the large pair, we will know in which order we're going to collect the critical points, and each critical point will appear, each bead will contain only one critical point, and in the bead, the map is going to be like a power map, and everything will be nice. So, and this lemma is a drastic difference compared to the unicritical case, because in the unicritical case, such problem does not appear at all. And now if we go to the towers, so if we consider a similar thing with the towers, with the towers, so we see that if so now we can go backwards, so like renormalizing backwards. So in the same picture as before, so the sizes of the beads are fixed, but we can look from them sort of from further away. And if it turns out that when we go backwards in the tower sufficiently far, and we see that in the backwards, well, part of the tower, the critical points are separated far away from each other, then again, the same argument as in the previous lemma works. So the statement is the following, that two critical points have asymptotically non-equal histories if the left parts of their itineraries differ at infinitely many positions. And if the critical points have pairwise asymptotically non-equal histories, then two towers with the same combinatorics are quasi-conformally conjugate. But if the histories of some 2 points, and this is why you see we need to have one critical point at 0 and two free critical points. If two free critical points have asymptotically the same histories, then there might be a problem. So this lemma does not say why there is a problem. So you need to construct an example. So since I'm completely running out of time, I will leave this slide, which describes the construction of the example, at least to some extent. Maybe not everything is written on the slide. But maybe I should stop here. So we do construct an explicit example of two towers with two critical points with the same history, which are not topologically conjugate. So let me stop here. Thank you.
Okay, are there any questions?
Thank you. So, did you determine the codimension of the stable manifold? Did you compute?
Oh, okay. So this is the part of well that I was not planning to talk too much about, but since there's a question, so I can say, so we have not proven hyperbolicity yet, but we think that we have the necessary ingredients, so we hope that it will work. And the dimension of the stable manifold should be equal to the number of critical points. And the philosophy here is that if you imagine two critical points which stay close to each other, then after renormalization, you rescale and they will move apart. So each extra critical point gives you an extra unstable direction. But there are other issues there which I haven't touched.
And the second question, is it natural to expect that there is a leading unstable eigenvalue? And would it be the Gaussian eigenvalue?
So leading unstable,
yeah.
Well, you mean that there are no multiple eigenvalues?
Well, as you said, there are several unstable eigenvalues. So is it natural to expect that there is one that dominates? And would that eigenvalue correspond to changing the rotational number, the Gaussian eigenvalue?
Okay, good question. I don't know. I haven't thought about it.
Well, I guess it's more like expectations.
I haven't thought about it, but thank you for the question. I don't know.
Question. So to clarify this construction of non-conjugated conjugate towers, your critical points have different, what did you call it, itineraries or sequences. So if they have the same, if all corresponding points have the same sequences, do you expect that they will be always conjugate?
So about the construction, well, if so the construction goes as follows. So we construct two commuting pairs with different combinatorics. So there's a blue one and the red one. So the corresponding two critical points have different combinatorics, as you see. It's very similar, differs only in the order of numbers 4 and 5 and the itineraries. So we have two commuting pairs with different combinatorics, which we renormalize, and we look at some particular omega limit points in the renormalization orbit of one and another. So again, these two have different combinatorics, but the omega limit points will have the same combinatorics, and these omega limit points will turn out to be different. So this is the idea of the construction. And so they are different, but if we are going to, but they are different, but since the omega limit points will have the same combinatorics, the same real combinatorics. If I renormalize the omega limit points, they will converge. The renormalizations will converge to each other. But nevertheless, in the attractor, these are different points.
I see. Thank you.
I have a historical question, in fact. So there was an a priori bounds for unicritical case in the about 1990, and then a priori bounds for the multicritical cases like 30 years after that. And so what was the reason it took that long? Well, compared, for example, to multicritical interval maps where it was obtained earlier?
Well, I don't know. Somehow, I think people haven't looked at multicritical circle maps for whatever reason. I don't know.
Okay, are there any fast questions? Oh.
There's one more question.
Thank you. So trying to understand your example there about the two different combinatorics and what it means. So if I am correct, then any two multicritical analytic circle maps, which are topologically conjugate, I guess, with the critical points going to the critical points, are quasi-symmetrically conjugate to each other.
On the real line.
On the circle, yes, on the real line.
Yes. So this is real bounds.
Yeah.
Yeah.
So what you're saying is that when you go and you try to explain the renormalization operator by complexifying, then you see this kind of different combinatorics, and these complex combinatorics actually do kind of persist, even no matter how or can persist no matter how long you renormalize. So this means that you have to change your theory somewhat in order to.
Well, so this is a little bit delicate. So maybe changing a theory a little bit, but not much actually. So this counterexample that we construct here is rather delicate, in the sense that if we look at the combinatorics of the two towers that are different. So the combinatorics will be, so let's say here I fix the rotation number with all 5s, and then one critical point will consist of, well, the sequence A infinity is just an infinite sequence of 1s. And here another critical point will consist of A infinity 1 and something else. So it means that the histories of the two critical points are the same, which means that if we backwards renormalize, then these points go closer and closer to each other. So this is the phenomenon of essentially understanding what happens when two critical points collapse onto each other. So it's not fundamentally new history, sorry, new part of the theory. So it's just the same theory, but the extra part of understanding what happens when two critical points collapse onto each other. And essentially it means that in this case, we have those towers which are described by infinite sequences, and in these special cases, when this happens, certain points in the combinatorial description of the towers have to be sort of blown up into several points of the attractor. But again, the phenomenon happens due to, well, essentially collapsing, like a bifurcation that happens when 2 points collapse onto each other.
Okay, thank you.
Any questions from the online audience? Maybe you can just unmute yourself. Okay, then let's thank Igors again. Okay, we have a 5 minutes break.